Thank you very much, Marco, and yeah, thank you very much for having me. So what I will do is I will go over the practitioner side of it. So basically, how we deployed what Marco did in the paper, what pitfalls we faced on the way, and yeah, what kind of our learnings are on that topic. So let's start with how it looks in the end. I think you saw some of the some of those graphs already in Marco's paper. The Latin spaces, of course, are always super nice to visualize something to people, because you can easily see, okay, I have lots of dark dots, which are basically where we have clusters of postings because we have a certain alpha blending to them. And then you have gray points, which simply show that there's like one single posting lying around there. And what you can see if you click them is that you as well end up with a high anomaly score. So those would be global anomalies. And then by clicking on the anomaly score, if I would be able to manage that, you can as well try to like figure out where you have local anomalies, which are in a certain cluster, but are somewhat fraudulent as well, or expected to be fraudulent. And as a user, what you want is basically like, okay, have a list of all the accounting or all the postings we saw, and just investigate one after the other. But the question is, of course, how do you get there from like having the paper to having a front end? You can basically give auditors to tell them like, well, this is 100 fraudulent statements we have. Do you mind checking them? So basically, let's start with how we got there. So first of all, what we do is we basically develop AI capabilities that make it easier for companies to run their ERP systems. And as Marco showed us earlier, one interesting point is the invoice payment process. So basically, someone sends you a bill and wants money from you. It's always a place where money leaves the company. So it's something you really want to pay attention on, because as soon as you paid a supplier, it's hard to get that money back. And there are a lot of cases where either people just invented their own suppliers and paid them and then left with the money, or agreed with a certain supplier that was already listed to give them 20% more and get half of the money that left the company extra. There's a humongous amount of ways to basically trick the system to get money out of the company. And one of the ways to avoid that is the anomaly check. And that's how we ended up stumbling over Marco's paper. And we're like, oh, we should definitely try to implement that and give that to users. So, well, okay, we found a paper with example code and readily converted data. So you could as well test that the paper worked. So kudos to that, Marco. It was easy to reproduce your code, certainly. But now, of course, the data are converted and anonymized somehow, because you don't want your financial records to just be open to the public. And you're actually not allowed to, because as a publicly listed company, if you release your financial statements, it's basically just leaking information about how much money you make. So the difference is we had a customer who gave us his SAP data, and then the first thing we had to do is like, okay, how do we get from the raw data to the converted data, and how we do that consistently? And the goal was to just provide a consumable REST API, because as Marco said, it's nice to do those analysis later. But what you actually want as an auditor is a small notification on your screen is like, someone tried to steal money from you. And that's basically only possible if you get a notification as soon as the posting enters your system. So to achieve that, we had one big issue, which I think is sometimes frowned upon by a lot of data scientists, me included, is basically doing reproducible transformations and doing them correctly all the time, and doing them the same in training and when we deploy everything to a REST API. So what we do internally for that is basically think about, we have two things. We have data containers, which just hold some kind of data, for example, a table. So a pandas data frame, for example, and they are stored in S3 or blob or whatever, maybe in your local hard drive. And then you have nodes, which you can think a bit of like scikit-learn transformers, which basically just take the data container and do something with it. Following always the Unix principle, they do one thing and do it well. So for example, something you always probably have to do is date transformations. You get a date time, but you want to have cyclic features because you want to basically check, okay, do I get this posting all the time on the last day of the month? You don't really care about the 31st of March 2021. You just care about, is it the last day of month? That's what a date transformer, for example, does. You want to embed the categories. So as Marco said, they used one-hot encoders. We went for embedding simply because they are a bit more resource efficient. And then when you've done all those transformations, you want to merge them, you drop them into the model, and then maybe log some information to MLflow. And the cool thing is each of those nodes just produces an output container and a storage container. And the storage container you get back when you get into the validation run, and the output container is just basically FYI, that's what I would have produced with the model. So for example, the compliance model has a storage container which stores a PyTorch model and gives it back to us when we go for validation or to inference. The cool thing with this is you can very easily test those nodes. Same goes for scikit-learn transformers. If you write such a transformer, the kind of cases you do with each of those nodes is innumerable. You can basically check that if you give not a time into the node, that it produces what you expect, that it does the same for certain dates. And you can then be sure that this transformer works all the time. As well, if you go to production, it doesn't break. I don't know how many of you deployed something into production, tried to do the same data pre-processing, and then wondered why their model wasn't working. It's, at least in my experience, most of the time the pre-processing pipeline, not the model itself. But if you have a black box like a model, it's always tricky to debug if it's the model or the pre-processing pipeline. So by properly testing those nodes, it helped us a lot in deploying the whole pipeline with the pre-processing. The cool thing is it as well allows you to like efficiently cache your data, because if you know that, for example, you do grid search over the compliance model, like Marco, for example, did a lot of tests with 10 or 5 or 2 Gaussian distributions in the adversarial space. Well, the thing is, you don't need to do all those computations again. You just take the data container you get here, you dump it into the compliance model, and it trains it. And you can just do just reuse those data all the time, which was kind of advantageous for us. We always implement a batch call and a call method, because if you do preparation in research, you most of the time just transform whole tabular data, which needs a humongous throughput because you don't want to wait. But if you go for event-driven or REST API where you just get single requests, so you normally just get a single posting and you want to reply immediately because you don't want to keep the clerk from working, then you want to get way faster in streaming data. And the cool thing is as well, it's easy to run that thing distributed. You can just package a node into a Docker container, and you can just drop the data containers to S3. So you can just run all nodes at the same time and just say, Kubernetes, give me extra nodes to like deal with extra compute nodes to deal with all my transformers. So one thing we use for training is Argo. It's an open source project for Kubernetes. You can just give it a directed acyclic graph, like for example, our pipeline. And the cool thing is it just starts every pod when all the predecessors are done. So if you look back at the pipeline, when the input data are present, it would just start all those 3 nodes. When all the 3 nodes are done, it would start this one, then that one, then that one. It's as well the backend for Kubeflow, which some of you might know. And the cool thing is you can easily scale it because you can just throw in hundreds of pipelines and train it, which is quite important for us because what Marco did in research is investigating one data set in very detailed. What we do is we serve more customers, so we need to get a lot of data sets through our pipelines. So we as well don't have this problem that we have only 10,000 financial records or the aggregated financial records. We have more like 30 million, and that's getting tricky to run on your local machine most of the time. Another humongous issue you run into is when you actually want to deploy the model. If you are in research, you always have this, how do my test results look like aggregated over all our data? What we actually need to give is a REST API, which is as well secure to be used by the user. So what we did for that is, we have the SAP system calling us and going into a load balancer to basically just be able to scale out this whole system. And then we give a private RSA key to the SAP system, which it can use to sign the request. And then we have an RSA validation system, which is basically checking if the signature is correct and what user sent the request. It returns us, yeah, okay, it's a valid user, here's the user, or it returns us a 401 if someone else just tried to access us. If we get a user back, we can as well check in the access control. Well, does the user actually is allowed to query this model? We implemented all of this with ORY, which is another open source microservice, which does all the authentication and authorization for you, which is super handy. And then once that is covered, we actually do send the prediction to the model and store the results into a Postgres database and send it back. The Postgres database is super important because what Marco said, for example, when the year changes, you get a humongous amount of changes or when the fiscal year changes, you get a humongous amount of changes in your ERP system. And you want to be able to monitor that and retrain the model based on the data you get, the new data. And the cool thing is you can use the data in the Postgres database to basically then retrain your model or partially retrain your model to as well work with like those shift in your data distributions. The neat thing is we can as well like utilize all the transformers we already tested, just convert all the pipeline to a Python function because the transformers just have methods for it. Which we can stack together and get one long Python function. We drop that on a fast API microservice, and then, as mentioned, have the Postgres database. The cool thing is you can scale all of that to handle spikes in traffic. One of the reasons why we run our backend on Kubernetes, and one of the reasons why I would urge everyone deploying a data or every machine learning model into a cluster to do it as a microservice. It just allows you to put a second, a third, a fifth microservice up when your traffic is spiking. And most of the time you have stateless models, so it's easy to as well just do make replicas of them. Which would lead me to the lessons learned. So one thing that helped us a lot when deploying this was working test-driven. So basically every of those transformers is tested, as well the compliance model. What we did is we just generated a data set which had certain clusters and certain outliers and just trained the model to detect that. So we were somewhat confident that the model can learn at all to get like the biggest bugs out of it. We as well realized it's somewhat hard to getting even great papers with like well-written open source code into production, because like research normally ends at the result where you say like, okay, I can do a posterior analysis and can say my solution would have solved the problem. If you actually go into production, you run into those issues of authentication, authorization, people want to hack you, and as well going really low in latency, which is especially the deeper the model goes, the longer you need for those predictions. We went away from Jupyter notebooks. Like they are amazing if you plot or pilot or want to explain something, but if you want to deploy something into production, the Jupyter notebook doesn't really help you too much because it's not easy to Dockerize or to reuse at all. We reused a lot of open source tools like Argo and OOY to solve the issues that we didn't want to solve, like the running of the acyclic graphs or the authentication and authorization. Being Kubernetes native helped us a lot to scale the model, while being as well able to just jump from one cloud provider to the next, because especially if you work with fiscal data, companies get very picky what cloud provider you are allowed to use. Like retailers don't like if you use AWS, automotive companies don't like if you use Google, and you can play this game a lot of like, I don't like that one, I don't like that one. So it's really important to stay cloud provider agnostic. And I don't know how many people of you use Terraform to deploy stuff. If you do, use the Helm provider in Terraform to deploy Kubernetes resources and not the Kubernetes provider itself. It leads to a lot of issues down the road. So that as well actually concludes my side of getting the model into production. If you have any questions, feel free to reach out to us, either me or my co-founder, David. And yeah, if you love Python, Kubernetes, or React, of course, feel free to reach out to us. We're hiring, as everyone has to close his presentation when working in a company. So yeah, thank you very much, and feel free to ask questions if you want.